Hey guys, it's been a while since I made a video. Things have changed quite a lot, but that's topic for another day. Anyways, so this here is 4B11T engine teardown, failure analysis, and yeah. So I was actually gonna leave this, but this is a very unique failure we got on here, which is something you probably weren't gonna come across anytime soon. So a lot of things going on here, and this is pretty much a perfect example of what we have to work with. Yeah, so let's just get to that. So first of all, car basically non-running, basically no compression on the cylinders, and there's a few reasons for that. But yeah, we'll go through everything now and just show you guys what's happening there. So first of all, we're going to look at the bores. So I did give these a slight hone, and immediately you can already see that there are some clearly worn marks there and here. And I notice there's a little bit of a line there. So that's something I'm going to chat about in a little bit. You can see them there, and there you see the same one. So previous guy that built the engine unfortunately did not know enough about what it was doing. They even put on nice fancy ACL race bearings on the rods, but never did anything to the mains. Anyways, and then obviously a few other failures we're gonna look at. And crankshaft here, crankshaft looks pretty much alright, so not a lot of damage there, but I do feel there is a bit of a ridge there, so we'll go through that. Just have a look at that. Pistons, these are the old ones that came out. Let's give them a bit of a cleanup. You can even see there's some machining marks there, so I don't know if they try to lower these a bit more, but there's definitely, they try to do something with it. And obviously, like, these are this one I didn't clean, so you guys can just see the rawness of it. A little bit of scratches there, just like try to get the carbon off to get the thing. So these are JE pistons, 2618. And interesting fact is that the Evo 10 came standard with 4032. So the difference being that 40 to 32 pistons have a higher silicone content, which allows you to run tighter clearances. So if you then go take a 2618 and you drop it straight into this guy without compensating for your piston to wall clearances, you get things like this. See that wear marks there? So there's a little bit of a coating here. It's kind of like tore that down. These normally have to do with clearance issues. Now this is aluminium alloy. Alloy is basically a mixture of metals regardless of what's in it. Alloy is just a mixture of metals. Aluminum alloy is mainly an aluminum part that has been mixed up with other metals. So here you can see the part number there for the JE pistons. Good quality piston brands. Personally, not exactly my favorite. Came with the car. They still look pretty good, all things considered. Probably could still run these if you really wanted to, try and save a buck, but we got some big plans for this build, so we're not going to reuse the old ones. And I'll show you now why exactly we're not going to do that. So we need to measure these, because anything without dimensions is basically just guessing. And we're going to use our micrometer setup here for that. You can pick up a set of these for relatively cheap. Obviously that's the one I use. I just normally keep things in plastic. Now with mics, people argue with me, but if you're working with precision, you've got to hold it with this little piece there. Reason being is because it doesn't let the heat from your hands go into the component, which does affect your accuracy. It does affect it. If you're running 2 decimals, probably not as much, but you will see a difference. So we use this nice little stand there to hold it in place, and then you have to worry about any of that stuff. Right, so we just put that in there, and then here we got our thing. So we got to set this guy up. When we use our little pressure piece there, and we would basically set that to 0 right there, and then we'd tighten it all the way there, and then we'd use this little line here if the camera will focus. There we go. That line there needs to align. Just ignore my messy fingers, they're dirty, engine stuff, And now I'm just going to set that up quickly, and I'll show you guys what that looks like. Okay, so with that adjusted, sorry guys, filming at night because the stuff's going to engineering tomorrow, and I need to get this done. So that's the proper measurement there, and you can see by thermal expansion of this component, I zeroed it last night or during the day, and you can just see how much it has increased there. So we're going to take our little tool, the forky tool, and just quickly adjust that. So I can probably try and film that. Let me do this quickly manually, and then I'll get back to you guys. Okay, so there we have it perfectly zeroed. You can basically, if the thing will stop reflecting, that line there is now sitting basically straight at 0. So that's the thing with your temperature. Now you know the temperature is right and everything is good. I'm just going to take that out. I'm going to do that first. There we go. Put that back where it's supposed to be. Now to measure the bores here, we're basically going to use our telescopic gauges. Now most engineers, they would use a bore gauge, which is really good, but they are really expensive, I'm assuming. No, let me just open this. Okay. Alright, and we're back. So we're going to be looking at 86 millimeters. We're probably looking at this one here, which being the second largest, I would assume is this one here. Righto. So these ones here, they've got two little thingies like that you press in, and then basically they expand and then go there. So what we basically do is, we know we're going to be in the 86 range. We're just going to put these in a little and then just nip that side there, just so it kind of holds them in place. Okay, a bit hard to do one-handed. Okay, right, so we've now basically bring those in, just give it a little bit of nip there. So these can still move if they're pressed on, they're not completely locked in place, and you'll see there's a thick side and there's a thin side. So I'll tell you guys what we're going to do with that now. So we're going to check first off for out of roundness. So we're basically going to put in the bore, open up this little side here, which will make them release to whatever side it is, and you want to hold it like a little angle, see it's not straight, and we're basically going to nip that in place and then pull it through like that, and that is your measurement. And then you're going to go to your micrometer and you're going to measure that. So let me quickly get a measurement for you guys on that. Okay, and that is our measurement. So we are measuring our distance there, which is 85, and then we have one notch over, so that's 86. The half notch at the bottom does not show, so we know that is 86.14, the sensors are 145. Obviously you could round up to 0.14 or 15, because I know that this product is going to be sitting at like 86.145. But yeah, so you can see, so that is our dimension. Now if you have been building on these engines, you know that clearance is quite excessive for what we are going to do, but we're going to measure it, we're going to calculate it, and we can look through all three. So what we're basically doing here with that measurement is we're taking one measurement, like if the damn camera will focus, and we'll take a measurement like that, and we'll take a measurement like that. So what are we doing? We're basically checking for out of roundness, and from previous measurements it was out of round, but I think we did that one. So let's quickly do the other angle. I think cylinder 4 was the worst of the lot. I think I measured 0.8 on the first time, so I think after the hone it had a little bit of a different effect. So with that in place, sitting at our 86 bore, nip it on the top, pull it through, we have that, and I can bet you this side is going to be different. Look how easily it slots through there. That's because differences in bores. So we're going to measure that quickly. Okay, camera's been out of focus as I just pressed record. Hello, here we go. So that comes in at 86, but look how it's below the 0, which means it's not 86, it's 85, and then that little bottom line at the bottom part of the line is 0.5, so it's 85.5 plus 45, 4453, what it looks like to me. But this, sorry, tiny thing is hard to focus on the camera. This is very nice to look at. There we go, there's a nice little view there. So there we can see 84, 85, 86. So this is 89, 80, what am I saying, 89, 85.963. Now that's very different from the long one, so which means I probably measured wrong. So we got to check our tips of the telescopic gauges that we're using here. Are they nice and clean? Are our micrometer tips clean? get a little bit of wipe there, wipe that off there, and just double check that again. Okay, and there we have pretty much 86 on the dot. So what does that basically mean? It means that on this side we measured 86.15, and on this side we measured 86. So the cylinder is clearly out of round. So what exactly does that mean? That means that the shape is not round. It's protruding more this way than that way. So if you were to take your piston ring, does this one have rings on it? Yeah, this one. So if you have the piston ring in there, let me quickly take a ring off and I can show you guys. Okay, so I just dropped the piston ring in there. Quickly, let me see if I can just indicate to you here. I'll just use the tip of this to show it. So you got the ring, and you can kind of see a gap opening up on that side of the ring. And notice how there's no gap on this side there at all, because with the light obviously it's a bit easier to see. So basically what happens is that your compression chamber gases can escape through those holes there. Was this the case for the failure? Although it looks like it, no. But that does affect performance. It will have a definite effect. Now the other thing I want to show you guys is, remember how we measured the bores coming in at, like, I think the biggest we measured, we did cylinder 4. Obviously you got to do all 3, but cylinder 4 was the worst of the lot, so we're going off that one. And now another thing I want to show while I'm on the topic of rings. Remember these little protrusions here? So this part here is not actually an indentation, that is a protrusion. So reason being for that is I will show you guys shortly. Okay, so I just had to go grab my little box there. So these are replacement ones. And a very interesting thing here, if you were to look at the, okay, this is manually. I'm not going with the JEs again. I actually wanted the Seiko, but couldn't get them. These are the best I could get where I live. Yeah, so if you were to look at your, I was looking at the ring position, right? So I disagree with the statement, but this is what the manufacturer recommends. Top compression ring gap. Righto. What do we have here? And what do we have there? Clear indications that the top ring is ring on the cylinder. So at least they got the notation right. So why exactly is that? Why do they use these ring positions that they recommend when clearly they were on the bores? That's because these pistons, 2618s, are built for racing high performance engines, right? They were not built to daily drive. That is why the factory engine, remember, as I said, came out with 432s. A lot of people debate about this. They always say 2618 is better. Is it better? Yes, it is, if you're pushing a 500 horsepower engine, and most people just don't. Reason being is that these metals are more ductile. Ductile means it can flex a bit more. It's got a bit of bend into it, and they can resist knock a whole lot better than the 4032s. So that's why the 2618s are normally used in high performance applications. This engine does not make anywhere near the power required for 2618s. Well, not yet, but we'll get to that topic for another day. So yeah, so that is why if you are building for street use and daily driving, you want to get a 432. Now granted, these are 2618, so you know, do as I say, not as I do. But you can just see the difference in quality on this one. And this is a topic for another video. We'll get to that on another stage. But this is the 86.5, and that's so. Was that the reason the engine failed? Because the pistons are wrong? No, that's not why the engine failed. Because plenty of guys are very happily running their 2618s as dailies, and they have no issues. So let's have a look what else is going on here. So let's look at the bores. Now you'll see these long scratches, not just the singular line, it's a long scratch. Keep in mind this is after I honed these, so all the impurities have already been like taken down. You can clearly see there's almost like a ring here, and then like a much darker ring at the bottom. You can really feel that protrusion there. That's really sticking out. Anyway, I digress. So you can clearly see they all have it, and then there, and then here, and then there, and here, and then there. So when we measure this, let's quickly do that. Let's measure our piston to bore, a piston to wall clearance. All right, so this is cylinder 4 piston we have here. Righto. We're just gonna slide that in there, and notice the play. That is your piston to wall gap, right? That was measured at 0.24, I think it is. So we took 86.5. So actually, let's do that quickly. So every performance piston that you'd have would have a certain point at which it's measured. Normally you'd have to look at here. So let's use the Manly ones as a reference here. Pretty happy with Manly as a brand actually, but at the end of the day, 2618 is 2618, doesn't matter who the brand is. The metal behaves the same. Just some people have a different, because it's an alloy, they have different additives and things. Some metals are more pure than others. Obviously at the end of the day you get what you pay for. Yeah, so obviously you got a whole bunch of like street strip, circle, like notice the difference here of the ring gaps and everything, all ring, but I'm actually looking for the bore, so I'm actually yeah, gauge point, right? So gauge point is where you would, now if you look at your piston, you got a whole lot of metal here at the top and very little at the bottom. So this is the top part is going to expand a whole lot more than the bottom part. If you have a standard bore, you drop these in, they will seize because this is going to expand. Now, one thing I didn't know of when I started doing this project, some manufacturers bolt their clearances into their pistons, and I think it's actually designed here. It's offset reduced connection rod. Where did I see it? It's somewhere here on the document. Probably some of you smarter guys probably like to see that. So so yeah, diameter measured, gauge point, bottom wall cylinder, finished bore side of the cylinder. So basically, yeah, there it is. Clearance is built into the piston based on the finished bore size of the cylinder. So in other words, when you put these in, you're going to have your excessive wall clearance because it works off the bore size there. So at the end of the day, I don't know how much miles the car is on it, it hasn't driven, so you're going to have a little bit of play on there, and that is where we believe the problem came in with this guy. Our piston to wall clearance on the 4B11T was too excessive. The pistons were good, they were measured into the difference that they have. So let's actually measure them and then we'll see where they are. So let's look at that area here and then that there on the gauge point that they show there. So just an indication, rough, so obviously don't take this as full truth. Anything information in this video is basically all full on your own risk, so do your own research. I'm just some guy on the internet that bolts cars. So let's quickly get this guy in here and basically have a look at that measurement. Yeah, so I've given this quite a few tries. So you can see there it's coming in at 85. We have the decimal here 0.5, so 85.5 plus the 41, it seems 40.5, so that's basically 85.991. Let's just say 90 for argument's sake, just to basically prove a point. So we now have 86.15 and we have 85.9. So you can work out that's 0.25 piston to wall clearance, which is in millimeters massive. It is far above what it's supposed to be, because these bores on this engine was just worn out from high mileage and they just basically need to get replaced. Replaced, what am I saying? Rebored to a better size, which is why we got another set here, which is, there's dimensions 86.5 to 1 inch. So we're basically going to take this in, we're going to take this to engineering shop. Obviously I can't do that at home because I don't have a massive machine that does this. There are, as far as I know to this date, no efficient way to precisely rebore cylinders at home. Can you do it at home? Yes. Can you hone them bigger? Yes. If this was a Corolla. This is not a Corolla, it's EVA 10. These parts don't exactly come free of charge, let's put it that way. So yeah, so we basically have measured those. Now we have our piston to wall clearances, we have our ring gaps and everything. Oh, we actually have another ring gap. So to measure a ring gap, I don't actually have that with me because I didn't plan on doing that in this video. Where to put the ring now? Where to put the ring? It's still on the board. Yeah, anyway, so you basically take your piston ring gap, where to put my ring. Let me do that quickly, just a moment. Okay, so it seems I've misplaced my ring somewhere. I put it somewhere and I can't remember where I put it. So yeah, I'll just quickly I guess I'll just have to explain it. So basically how I had them inside there, when we check the gap there, we basically measure your ring gap distance there with a feeler gauge, which I didn't plan on putting that in this video. So yeah, that's basically not in here, but I'll probably make a better video when we do assembly on this one. And obviously with the rods, when we did assembly, I think it was this rod here actually, where they had assembly failures. Let me see if I can just let me just undo this quickly and I'll show you guys. So yeah, we even got the ARP 2000 studs in there. So you know, like, they had the right idea, they just didn't have the experience on that. So this is kind of something that made me cringe when I first started working on this. Now if you look at the bottom part of the cup, notice how there's let's do this here, 2 dots on the left side of the rod and only 1 on the other side. Why is that? That's because they put these rods on the wrong way around. So when these rod caps are made, they're actually made as one piece. Let me see if I can just put this down in the box here. So they're actually made as one piece, and they're machined in the factory to spec. So they basically bolt this thing together, they drill a hole and they machine it into the spec that it needs to be. And if you go and you put these on the wrong way, as this or that, they don't go on the right way. I do think the bearings will actually show that. So you can see, so are these still usable? Probably. Just given the amount of money I've spent on this thing, I'm not really gonna mess around with other things, because the guy that built this really should have seen. Sorry for the focus, guys. The guys that built the engine really should have seen, like, hey, listen, something's not right here. I probably should stop tightening this thing. But they didn't. They just like went full send, kept going. And to be fair, the car ran pretty much okay with this. You know, we have very limited wear on the crank journals. There's a little bit of wear, but I just would attribute that to normal wear and tear. I reckon the car's probably got high mileage on. I actually haven't even checked the mileage in the car that I've got. I'm probably the only guy on earth that buys a car without worrying about the mileage. So you know, they are pretty much okay. They're not that bad. I think they assembled it, realized their problem, and then corrected it. But you know, damage is done, and that's so. Watch out when you guys rebuild it. Caps always go on the same way. Do not do that. As a rule of thumb, when you take them off, take out a little marking pen, mark the edges. Normally they would have some form of indication to show, like, hey, listen, this thing goes in one way. Let's see if that's there. This side versus the other side. So normally you can see, let me just quickly assemble this rod. Okay, right. So normally if you have assembled a rod, you can feel like there'd be like a real smooth finish there. If your fingernail catches on it, it's probably not right. You can also see with the edges there, so these shapes here would line up nicely. Yeah, so like this side shows it better than the other side. And you can kind of see, you know, which one is the good. Now on some engines you'd have a small little taper there, which is not present on the other side, although most engines these days are, you know, they're all the same, symmetrical and that, so you know, you can't really use that old guide rule anymore. And obviously, you know, as you tighten these, they will basically flex to position. We are getting some I-beam rods on this one, but there'll be more about that in the next video with the engine reassembly. This is basically the failure analysis. Now there's a lot more I wanted to go into, but unfortunately, you know, I did run out of time. These things got to get to the engineer by tomorrow morning. I'm a little pressed for time to get this done, which is mainly the main thing with the videos on the channel. You know, it just some of the stuff just isn't never completed, and you know, videos get cut off halfway, and then the car has to get out back to the client. You know, there's just no time to really, you know, do proper videos on this. Hopefully that'll change in future. This is definitely want to be in one of my longer videos. But I do feel like it's a really good indication of what you can see. You know, you can see the wear on the bores. My words getting mixed up. You can see the ring indication. Now normally with the rings, I would have them at like 120-degree angles, but with performance you want it in that range, because when you have the boost coming in, as that piston pushes up, it's going to push against the wall, pushing out the ring a little bit more. Personally, I don't like to do that. I like my rings to overlap, so you get smoother areas here and you don't get things like that. So this is one thing you need to also look at. You can even see like it just goes up, and then just like stops on pretty much all of them. Like it just stops there. So again, that's what the manufacturer recommends. Maximum seal, definitely. But yeah, that's one thing. So interesting concept. Out of round versus oval. I think it was out of round versus I forgot what the other word was, but out of round, it means you can visually see it with the eye. The piston to wall clearances on this one, your out of roundness tolerance is 0.1 millimeters, so still kind of just over the edge of the line, so we are kind of out of spec with that. Anything under 0.1 of out of roundness is pretty much acceptable for this engine, with the specs I remember correctly. Piston to ring gap, 3.5 thou. What's again? Just quickly double check for some of the guys. Maybe you guys are building an engine, you need to get some piston specs and things. So it's pretty much the same as this. I'm going to build my engine to these specs. So obviously we've got a lot of plans for this, and I don't want to be doing this again twice. So we'll possibly be running gauge point, piston to skirt. So here's your wall clearances. We're going to do a 0.4 thou. I think it was 0.3. There's a Mitsubishi. Yeah, there, Mitsubishi. There we go. I don't know why anyone would want to own a Mitsubishi, but anyway, we do. That's what we do. We have coated skirts, so we're running 0.035. That's recommended. We're going to be running a little bit of higher boost, so we're probably going to go to 0.5. But I think I'm still deciding if I'm going to go 0.4 or I mean, if I want to go 4 thou or 3.5 thou, probably going to run with 3.5. It's probably going to be better. That's what we're looking at. And then ring gaps, we are going to be looking at high boost on top ring on that 0.08 inch times the bore. So worked out to 3.5 thou on the piston ring gap. So that's what I'm going to be running. So 3.5 thou pistons ring gap on 86.5 times that, and then just convert that back, and then 3.5 thou on the walls. I do want to run my clearance a little bit tighter. I will sacrifice a little bit of performance for that if needed. I don't want the piston slipping around. So as these ones are cold start, you could get it like walking up the bore, which is what I think also happened in this case. So keep in mind, guys, if you are building one for street use, try get 432. I know Vossner in the UK, they've got a very good deal, very good quality set for 4B11T. They were the only guys I could really find with a 432. It's kind of few people actually do it because they all want to make high boost powers, and then they build their 1,000 horsepower rods, and then they never tune it above 250. So yeah, that's one thing to look out for. And then obviously 2618 is basically a racing piston. They do wear out your bores over time, like what happened in this case. So this what here is exactly the reason why you do not want 2618. Unless you mind rebuilding an engine every now and then, if you're a weekend warrior, you like messing with engines, probably you don't have a problem with that. Probably good with that. But if you don't want to rebuild your engine, I mean, being honest, this 4B11 is really a pain to get out the Evo. It's I've got the MR, which has 7 bolts on the transfer case and not 6 like the others. Not to mention cracked manifold here, so I got another little crack running there. That has to get probably fixed. I'll try and get that fixed, if not replace the whole manifold. You know, so it's really not exactly a cheap thing to work on, but at the end of the day it'll work out. So yeah, anyway guys, I'm gonna wrap it up. Video's getting long. That's basically engine teardown, fault finding on the 4B11T Evo 10 MR. Yeah, so we're gonna call it quits there. I gotta get these things tacked up, bagged up, and get it to the engineers tomorrow morning. It's now just past 9, I think. And yeah, finishing up for the day. More videos will come soon. I'll probably will have a full engine build up on the 4B11. We can do timing, we can do turbo setup, we're gonna do wall clearance. We've already done wall clearances now. Probably set up the bearings, because I still want to check, you know, if I need to oversize this or if I can just polish away. And I think I probably could just polish away, keep it standard, because you don't want to cut away the crank. Could affect performance. But yeah, anyway guys, I'm gonna wrap it up there. I'll try and get more videos up in the future, and then so far so good. Anyways, take care, drive safe.